Okay, so as the title suggests, today we're going to talk about probability mass functions. You'll also hear them called probability density functions. I think that means pretty much the same thing. I've heard them called both. I don't know which one is better mathematically, and I don't really care. I'm much more interested in using these things as tools. That said, if we're going to understand how this stuff works, we're going to have to get into some of the math behind it. Today, I will mention the word calculus a couple of times. If you don't know calculus, it's not going to hurt you in any way. It might help you, though, if you do know calculus to understand some things. Okay. Oh, it comes up really slowly, eh? Okay. So you can plot the probability of a given score for any variable. Doesn't matter what the variable is. You can plot the probability of a score, right? And the probability of all possible events, all likelihoods, equals 1, because probabilities are out of 1. When something can't ever happen, it's 0. When something is sure to happen, it's 1. Well, it's sure you're going to get one of all of the possible events. So it's clear that the probability of all possible events equals 1. Okay? Okay. This is one of those cases where it would really help if I was in a classroom and I could even just see your eyes, because then I could go, okay, they get that. However, I think you're probably pretty good. So that means if we were to plot a curve, right, of all the possible outcomes, all the possible events of a variable, the area under that curve would be 1. If we were to measure it, if we were to take out a ruler and just figure out what the area was, it would be 1. Are you with me so far? Do I have any questions I can answer so far? Okay, good. Okay, let's say we had a die roll. And there are 6 possible outcomes with a die. You can get a 1, a 2. This is a 6-sided die, not a 24-sided die that you use playing Dungeons and Dragons with your friends. Okay. A 6-sided die, a 6-sided fair die, is equally likely to end up on 1, 2, 3, 4, 5, or 6. I was going to make fun of people who play Dungeons and Dragons, but I play a lot of video games and people could make fun of me. That said, I don't care if you make fun of me about playing video games. I have almost a 50,000 Xbox Live gamer score. So, I'm pretty important. But think about this. We got 0.16, right? That's 1 out of 6. There's a 0.16 probability of any single roll, right? 0.16 plus 0.16 plus 0.16 plus 0.16 plus 0.16 plus 0.16 plus 0.16. I think I did that 6 times. If I did it 7 or 5, my mistake. It should be 6. But if we do 6, right? There are 6 possible rolls. We multiply that times 1 over 6. We get 1. So what I'm saying is, if we were to think about this thing as a curve, the area under all of those bars added up together is 1. Okay? All right. So that's just some background, and that's stuff I'm pretty sure you know, or you've been taught in 2126. I think you were if I taught you. Probably if Dwayne taught you. That said, refresher. The point of these first few lectures of this course is refreshing your intro stats and getting in at a bit of a deeper level. Okay, let's talk about the normal distribution, right? The normal distribution. That's the normal distribution there. Where did I get that picture? I don't know. I think I Googled normal distribution and I found this one. And as you can see here, this has mu, and this has, this is actually a standard normal because it's got 0 and then 1 for 1 standard deviation, 2 for 2 standard deviations. That's a standard normal distribution. Let's put that over there. Make it a little smaller. So I would say it's the most common distribution that we would run into in a course like this. Yeah, the F distribution, the T distribution, chi-squared, they all are derived from the normal distribution. And remember, they're just probabilities of given z-scores. Remember z-scores? All those are probabilities of given z-scores. That's all they are. Okay. So for us, it's probably the most useful. And it may not be the one we run into the most, but everything that we run into in a course like this is based on this distribution. So the chi-squared distribution is, for example, okay, a chi-squared distribution is, say with 3 degrees of freedom, is 3 normal distributions squared divided by 3. The F distribution is 2 chi-squared distributions divided by each other. Like, and when they all come from this, they all come from here, okay? So the characteristics of this distribution are that it's unimodal, and you can see that it's got one mode. It's symmetrical, it's the same on each side. And it's bell-shaped. When we can talk about, we can describe the shape, describe the spread, and we can describe the central tendency, we've basically got the 3 things we need to do to talk about a distribution. So I've told you the 3 things, and these are, of course, all 3 things that you already knew. Any questions at this point? Just speak up if you got one. Okay, good. So you might ask yourself, why is this useful? I know when I took undergrad stats, I often asked the questions, why do I care? And eventually I got told to stop asking questions. I kid, obviously, but I did often ask these questions to myself, at least. And then oftentimes at office hours with my prof, I would go and ask, why do we have to know this? How does this fit together? And I had some pretty good stats profs as an undergrad. Many variables are assumed to be normal in the population. Note I said assumed. You're told a lot in 21-26 intro stats classes that, everything's normal, everything's normal. It really isn't. A lot of things are, but a lot of things aren't. You know how you're given, if you look at review questions in intro stats books, or you look at practice problems, and they say light bulbs have what's the word I'm looking for? A life of so many hundreds of hours or thousands of hours, with the mean of this and a standard deviation of this, and it's normally distributed. There's no way light bulbs are normally distributed and how long they last. Because if they were, that would mean there'd be as many shitty light bulbs as really good ones. And do you think GE wants that to happen? No, I'm sure it's extremely skewed to the right. Right? It must be. I'm sorry, it's the left. Yeah, the tail tells the tale. It must be. Or they go to business. Anyway, doesn't matter. The point is, there are a lot of variables that are assumed to be normal in the population, and a lot of things that actually are normal in the population. Sometimes we design them. IQ is normal in the population because the tests are designed to be normal. Right? If we can design a test and make it normal, if we can design anything like that, we do that a lot in psychology. We design tests and say, we can figure it out and say, this is a normal distribution for this characteristic, whatever it's supposed to be measuring. The great examples, IQ. So we can use standard techniques. The important thing here is that there are standard techniques that reference the normal distribution. So we're going to use those. Now, okay, this is where it's, so far, I don't think there's any issues. We start to get to some issues when we start to think about sampling distributions. A sampling distribution, let me bring up the bottom part too. A sampling distribution is the distribution of all the values a statistic can take. You all know from the last quiz that statistics are numbers that represent samples, and they're used to estimate parameters. You don't just know that from the last, from the last class, you was asked in the last quiz. So the neat thing about sampling distributions, all the possible values a statistic can take, because statistics, the numbers don't know where they come from. So if you took a whole bunch of means with an N of 10, so you keep sampling. This is my pantomiming sampling. I don't know why. You would get one time, let's say it's heights. Let's go with heights, right? Heights are nice and easy, and we can think of students at the university. There's what, 2,500, 3,000 of us? Well, if you, I'm not one of you, I'm one of me. But we can look at heights. What's the average height of a human? Let's say it's 100, and let's just make it only women, just for the hell of it, just to make our sample. We're going to just truncate a little bit. So what's the average height of a woman? I don't know, 175 centimeters. I made that up. I don't know, but I'm going to guess that's what it is. Okay. Sometimes when we sample 10 women who go to Algoma University, on average, what should we get? Well, we should probably get 175. But sometimes we're going to get 190, a bunch of really tall women. Sometimes we're going to get 100 and, let's see, 160. So that's not very tall. So we 190, maybe we sample the whole women's basketball team. It just turns out that way. Of our 10 people there, they're all members of the women's varsity basketball team. If that's the case, we're going to get a higher, because basketball players are taller, we're going to get a higher number than we would expect. But what we're going to get on average is around 175, which I said was our mythical mean. But if we keep calculating means of 10 people, we're going to get what's called a sampling distribution of the mean in this case. And the central limit theorem, the central limit theorem, remember that from the undergrad, this is still undergrad, David, from intro stats, says that the sampling distribution of the mean will be normal. That's what the N stands for. Have a mean of mu sub x bar, or sorry, mu sub x. So in our case, that would be 175. And a standard deviation of sigma squared, that's the population standard deviation, divided by the square root of the number of observations. That's just a thing. And like I said, if you can sort of think of this, let's draw a little picture. Sometimes we're going to get, let's draw here, let's use a different color. Right around 175. Sometimes you're going to get a bit higher, a bit lower, a bit higher, a bit lower. And eventually you end up with something that looks like that. It's normal. And that doesn't look necessarily normal. It does when I put the extra lines in. But you would get a normal distribution. I encourage you, if you feel like, if you don't believe this, you can either just believe me. You can just say, oh, Dave must be right. Why would he lie to me? And that's good. I appreciate the faith. Thank you. But you can prove it to yourself. Roll a die. This is if you have a little bit of free time, okay? And I know you aren't loaded with free time. But if you've got a bit of free time, roll a die 5 times and get the average score. Average roll, and then do it again and do it again. Do that 30 times. Okay. You will find you will get an average, you will get I can actually tell you exactly what you'll get. Let's see. You will get a mean of 3.5 and you'll get a standard deviation of 0.16 times 0.84 divided by the square root of 5. That's what you will get, or something. You'll get something extremely close to that. There's a way to figure out the standard deviation, and then which I did when I was doing that 0.16 times 0.84, and I divided by the square root of, and you will get that. It's very cool. It'll surprise you because you'll get runs of like, oh, I got an average of roll of 6, an average roll of 1. And then you'll realize, oh, I'm usually getting around 3.5, which is exactly what I would expect. It's very cool. Okay. So let's take a look at any distribution. So we'll leave the normal distribution for a second. If we were trying to find out the probability of getting a score between 3 and 7, so that's 3 and 7. Is that a song, 3s and 7s, right? Queens of the Stone Age. See, I'm hip with music from 20 years ago. Well, how are we going to find this probability? The probability of getting a score between 3 and 7? Well, there's actually a pretty clear way to do this in this case. You're finding the area under the curve. In this case, it's actually pretty simple. I should go back, actually. We have a rectangle, and then we have a triangle. You may not remember all these things, but I'm sure you remember rectangles are length times width. And then triangles are half base times height. So you could do that. Remember learning that back in elementary school? You thought I'll never use that unless you have to buy flooring. Well, there you go. Very nice. You could do that. So it's simple geometry in this case. You could just get the area under the curve there. It's pretty simple. It's just really very straightforward geometry, right? That's something you could do. What if it's not a common shape? So what if it's a normal distribution? So it's not this weird triangle distribution that I've invented that I've never seen in the wild. This is where calculus would come in. So that's an integral. Don't worry, I'm not going to make you do calculus. If you've done calculus, you know what this means. If you haven't, you can go to sleep for the next 40 seconds. All this says is I'm going to find the area under the curve. I'm going to find a function that tells me the area under the curve of the function I have between 3 and 7. And those of you who have taken some calculus know that actually that's really not that hard. Integrating it's not as fun as you're saying, Dave, you find calculus fun. It's not as fun as doing derivatives. I think doing derivatives is more fun. This involves, I always found this harder when I was in undergrad math. Dr. Big Shot here, you know what he did in intro for his first year? At Western, you have to take a math class before you take a stats class, which I'm not opposed to the idea. Most people would take either linear algebra or they would take math for social science or for non-math majors, right? There's a course called Math for You, but you know what I did? I took calculus for math majors because I'm an idiot. You know, somebody could now throw in the chat, you're not an idiot, Dave. But anyway, I took that, and let's see, about 6 weeks left in the course, I stopped understanding what was going on. I did really well for the first, it was a full year course. So for the first 4.5, 5 months, I was gold. I was smoking it. And then I was like, I am sorry. I have literally no idea what's going on. And I had this great math prof, Dr. Kochman. He wrote the book we were using. So good. It was wonderful. And he said, I remember he knew all our names. There were 200 of us. And he knew all our names. Thank you, Evan. It's very kind. And he was an older Orthodox Jewish man. I knew that because he wore a yarmulke and he had a prayer shawl on, long beard, and a killer math guy. Like he really knew his stuff. And he knew all our names. And I went to get up to leave. This was like in late March. And he said, Mr. Broadbeck, where are you going? And I said, I'm sorry, sir. This is not on you. I've tried this so many times and I just don't get it. So my time is probably better spent at the student pub. So I'm going to the Spoke, which is one of the bars at Western. And he said, well, good luck then. But it was great. Mr. Broadbeck, where are you going? I ended up doing okay in the course, but that was totally based on all of my work up to then. I do not suggest getting up and leaving a class. It's not the best thing, but I was so frustrated. It's in first year and all these math majors are sitting beside me. And I'm like, I don't know what I'm doing. Anyway, you could do this. And it's a skill you can learn. Like there are courses, you can learn how to do calculus. That said, I'm sure we all don't want to, if you haven't learned to do calculus before, you would have a bit of a problem with this. So you're saying to yourself, I don't know calculus. And my answer is, well, that's your loss. Calculus is really beautiful. It's actually really cool, beautiful math. But you know what? We can maybe do this without worrying about calculus. So we're going to find out the area under a curve without having to do the calculus because somebody did it for us. Yay. So here's the normal distribution. That's the function of the normal distribution. F of x or y equals 1 over sigma a over sigma, which is standard deviation, divided by the square or times the square root of 2 pi times e. E is a mathematical constant. It's the base of the natural logarithm. It's roughly 2.71828. We'll talk more about that when we talk about transformations, but don't worry about it. To the exponent of negative x minus mu divided by 2 times the variance. Now, if you do know some calculus, you're going to look at that and you're going to go, that is not an easy integral. So doing the integral, finding the area under the curve using all these cool techniques, this is really hard. This is hard for a lot of people. This would be hard for anybody who's knows how to do calculus. This is not an easy integral to take. So you just take the integral of the function. I like how I just say, yeah, you just do that. This is a non-trivial task. I'm not going to go into why, but that's really hard. So say you want the probability of somebody having an IQ between 95 and 107. Why would you want that? Because you're doing a statistics problem. No one ever asks questions like this in the real world. but they come up all the time. And in stats questions, between 95 and 107, just take the integral. It's easy. It's actually not easy. In fact, I remember trying to do this in Dr. Kochman's calculus class. It was used to be called Calculus 27. It's not called that anymore. And I remember him saying, at one point, he was going through it to show us that it was hard. And then he said, by the way, this is almost impossible. So it's kind of, God, he was a good math teacher. I'll never forget that guy. Geez, that was 1985 that I got up and said, I can't do this anymore. And it still resonates with me. That's how good his teaching was. And I sold my calculus book, which I wish I would have kept it. Anyway, beside the point, this is not an easy thing to do, but assuming one could, you would take the integral and then get 95 to 107. This can actually be made a little bit easier. If we make the mean 0 and the variance 1, like a standard normal distribution, a Z distribution, we get a somewhat simpler equation, and we actually get something that it's easier to take the integral of. That's easier. All I've done is set the mu to 0 and the standard deviation to 1, and all the sigmas go away and all the mu's go away, right? This is actually doable, this one. This isn't virtually impossible like it is for the regular equation of the normal distribution. This is something actually you could do in a first-year calculus class. The last one you probably couldn't do. So all we've done is turn a normal distribution into a standard normal distribution, and it makes this easier. Don't worry, you're never going to have to. I'm never going to ask you what the function of the normal distribution is. This is being done to show you the background of why it works. The point of this course is not that you can discover new statistical techniques, okay? So still, it's not super easy, but if we turn this into Zs, which is what that is, let's just pull that up. This is why we standardize data using the Z distribution. It makes it easy. We have now a distribution that's normal and a mean of 0 and a standard deviation of 1. Now, I'm not going to go into a long thing about how one does looks up things in a Z table, because I know you all know how to do that. It'd take a little, and I'm going to show you an even better way to do it, which is there's a website you can use that's just nice, that's beautiful. But if we were to do this, we would find out the probability of getting a score between, in this case, what do we have here? We got a Z of negative 0.32 and a Z of 0.466. And I went through and I found out the probability of getting a score between negative 0.32 and positive 0.466 is 0.310. So 31% of people then have an IQ between 95 and 107. Okay, so that's what that says. I wouldn't get too worked up over being able to do this kind of thing, because it's something you already know how to do. If you sat down for about 15 minutes, you're looking at this now. Some of you took 2126 last term and could just do this right now. Others took 2126 first term last year, and you're like, that's hard, but you remember how to do it. And again, I'm going to show you a pretty quick, easy way to do it as well. The beautiful thing is, well, I have a statistical calculator, and it's not, I mean, it's a calculator that can do statistics. We can call it a statistical calculator. And I can actually put in two Z values, and it'll tell me the probability of those two, of the score between those two. You don't really need that. I bought that calculator in 1988. You don't need it because we have these tools on the internet now. There was an internet in 1988, but not very many people used it, and it didn't have a beautiful interface like it does now. It also wasn't full of hate propaganda, so the internet was different. Right. So someone actually did the calculus for you. When you look stuff up in a Z table, you're finding probabilities of scores. Think about this. Just draw a quick picture here. When you look something up in a Z table, you get, okay, so you look at the top of the table and it shows you this. So it'll give you, there's the X and there's 0. And then you look up the probability of getting a score between 0, like the mean of 0, and X. And it tells you what that is. In fact, there's always a shaded thing on the table, isn't there? And then you look up a probability. That's the area under that curve. You're literally looking up someone else's calculus, someone who did this a very long time ago. A long time ago, someone really nice did some calculus for you. Every time you look something up in a table, I want you to sort of think to yourself, thank you to who, you never know who it is. It's usually some poor grad student in math who did this in the 1800s or early 1900s. And you just should say to yourself, thank you. Thank you. I don't know, Steve. I just assume people are named Steve when I don't know their name. So Steve and Stephanie. So it's the two of them, the two male and female graduate students, looked this up, worked this out for you. So you can do it. Pretty cool. So now you can just look it up in a Z table because the calculus has been done for you. But when you look something up in a Z table, the thing behind that is actually calculus, is integral calculus, is someone finding the area under a curve between 2 points. Okay. Any questions I can answer at this point? Okay, good. I always figure at this point when no one has a question in any class, but especially in a stats class, either you get it perfectly or you're completely dumbfounded and don't even know what to ask. I choose to believe that you get it perfectly. You can also use this little web tool here. Now, let me just see if I can, that should pull that up. And I'm going to now share a different screen. So we're going to stop sharing this. And instead, I'm going to share, we'll just go to this whole desktop, right? Yep. Okay, so check it out. We've got, is that showing up? Yeah, it is. Okay. What were the scores? They were between. So we're going to go look at between. Was it, what the numbers again? 90. So 97 and 105, is that right? Or 110? Let me see. Oh, I can, what am I doing? It's not like I don't have that on my computer here. Let's go over here for a sec. Sorry, it was 95 and 107. Okay. So let's change this to 95 and 107. And our mean is, now this is IQ, so our mean is 100 and our standard deviation is 15. Oh, look at the number, 0.31. Now let's do it with a Z, right? And you'll see that it's exactly the same. So it's 95, so it's negative 0.32. So negative 0.32. And what's the positive? It's 0.466. And now we have a mean of 0 because it's a Z distribution and a standard deviation of 1. Oh, look, it's the same score. See, it works. It works. So that tool, that web tool, is even easier than using a Z distribution, like a Z table, right? It's even easier than using a Z table. Oopsie. Little mistake there. Right. So I meant to hit the share button, not the recording button. Okay, so back to sharing. Yep. That. So you can just use that, and I've now also just revealed if because the link doesn't work on the PDFs that you download, but you do have this. This is the actual link, right? Not just the underneath this. So this is in fact what you go to. There's all kinds of really good tools there, and this guy has had this there for 20 odd years. He writes a stats textbook, and there's all kinds of great tools there. So it's good stuff. So the beautiful thing about this is what I'm trying to show you here is that the thing you look up in a Z table is the same as the thing you get in that tool, but it's also, all we've done is transform it from mean of 100 standard deviation of 15 to a mean of 0 standard deviation of 1. Okay. Any questions I can answer so far? All right. Oh, look, here it is here. The only difference is up until a couple of years ago, it wasn't black, it was blue. So this is just a screenshot from that same website. You just saw what it looks like. So this is all something you can do. This is really just straightforward calculus. Straightforward arithmetic. The calculus has been done for you. The calculus has been done for you. You don't have to worry about looking things up in Z tables really if you use this web tool. But if you don't have the web tool handy and you have a stats textbook on you, you can always look stuff up in a Z table. And the beautiful thing is, if you don't have your stats book and you forget this web address, Google Z table. You'll be able to find a Z table. It's not like this is special secret knowledge that no one would know about, right? This is things that we all know, that it's all available. And it's, when you practice it with it a bit, just play with it a bit, it's really easy enough to do, right? So using this knowledge together with the stuff we talked about with hypothesis testing, this eventually will allow us to make probabilistic statements about how likely it is that we got a certain mean, right? Hey, look, my God, it's quick today. It's 20 to 11 and we're almost done already. That's wild. Okay. But we can always do a little bit of review if you want afterwards. Good. So some poor person did the calculus for you. So seriously, I want you to think to yourself, and I do this, I honestly do. Whenever I look something up in a table, I think to myself, thanks, buddy, whoever you were, for doing this for me so I can look things up, for making my life just a little tiny bit easier. So we just look stuff in as a table, or we use a handy dandy web tool like I've showed you, but it's still all based in the same thing. It's all about area under a curve and the idea that those curves show all the probabilities. So the total area under that curve is 1, and then we want a little sliver of it. It's just a probability. Okay. This isn't scary, or it shouldn't be. In fact, you know how to do this already. You must know it, or you wouldn't have the prerequisites for this course. And that must be disturbing, just my mouth open like that. You already know how to do this. Now you know why it works. Now, if I taught you 2126, you saw something very similar to this, though I don't think I went into quite the detail about the calculus and all that stuff. I don't know what Dwayne does, and it's not my business, but this now is why it works. And one of the important points of this whole course is, you know, in an intro stats course, typically you're told, do this when the world is like this, do this test. When the world is like this, do this test. The point of this course is to say, here's why you do that test. And the why is never because I said so. The why is it's appropriate under these conditions, and here's why. Right. And here's mathematically why. All right. Do we have any questions on this material? Because we're done really quickly on this, but we can do a little bit of review afterwards if you want of anything. Any other questions you have?
I just have a question in regards to using the Z-score table.
Mm-hmm.
This might be stupid, but I
don't say
how
that.
to use it. Could you?
Can I show you how to use it?
Yeah, if that's okay.
Yeah, it's fine. I just got to think if I have a stats book around that I can go grab. Yep, just a sec. All right, what I'm gonna do first off though is I'm gonna stop the recording because I don't think this actually is super useful recording wise. Well, no, I'll leave it on. Okay, so look what I have found. So let me just go to the Z table. Just gotta find it. Where are you? That's the T. Squared. Ooh, there's that. Is that there? That's the T. This won't take long, I promise. Critical values of chi-squared. Where the hell's the Z? Then it's T. There's everything in here but what I'm looking for. Oh, I think I just found it. Aha! I found a table called the normal distribution. Okay, this is going to take, I can probably do that from here. So what I'm going to do is I'm going to kill this share. And then I'm going to open up this camera. I think that should work. No, whoops, cancel. No, instead of that, I'm going to try something interesting here. Let's see if this is going to work. I do have a bit of a setup to make this go. Make us go. Make us strong, Geordie LaForge. There we go. No, it just crashes. So I'm gonna have to leave the meeting from this one. Okay. Yep. Good. Try again. Okay. Now let's try something. So we're going to go to share screen, advanced, second camera, share. Aha! The hardest part of this is me holding my phone steady. So we have here the smaller portion and the larger portions. Remember I said we got a, what's the word I'm looking for? Just a shaded bit. So this is telling us, we got to do this. The smaller portion, larger portion. Let's look up a Z value. So if the Z value is, let's say, well, here's one here, 0.36. The larger portion, whoops, it's hard for me to, I'm trying to do this by looking, it's like I'm doing the weather. There's the probability of this bit here. And the smaller portion, there's the probability of getting a Z of bigger than 0.36. Okay, so there's the Z score there. And that just tells us, let's use this. So now it tells us there's the Z, right? And then it tells us, boy, this is hard to do. The values, so that's the mean to there. So that would be from 0 over. But the important thing here is the larger portion, the smaller portion, and you can just see that from the graph here. So you just look those up and it tells you the probabilities. Okay.
Okay, thank you.
Really? Did that actually help? Good.
Yeah, it helps that I can like see it.
Yeah, I mean, it's one of these things I know, and you know you've done it. It's been a while, right? But it's totally something that is doable. It's a matter of sitting down and doing it. I wouldn't get too psyched out about this. It's more a matter of getting used to doing this kind of stuff. And just, if you do a couple of these or one of them, in fact, just follow along with the example I had in today's lecture, you should be able, you look at that and go, oh, I see what happened. And even if that doesn't, if this isn't something that you're used to using and it feels a little bit weird, instead of doing that, use that web tool. All right, so let's put this back here. Close this. Put it here. By the way, here's my view of everything. Okay. There, and we're going to go like that. And the share is finished and we're good, right? Yes. Excellent. Other questions? That was, I'm amazed that worked so well. I mean, it didn't work great, but it worked better than I thought it would. Okay, what I'm going to do is I'll stop the recording, but if anybody has any, want to hang around a bit and ask any questions, you can certainly do that. So let me stop this.